This video introduces the idea that we can come up with higher order derivatives. So rather than just dy by dx or d2y by dx, we can go to the third derivative, or actually the fourth, fifth, the sixth, and so on. Here's the general arrangement for the nth derivative. Why do we want to do that? The particular application that we are going to be looking at in this next part of study is Maclaurin's series. Maclaurin's series allows us to approximate functions, and as part of that, we have to be able to come up with higher derivatives. So these next two examples allow us to practice the skills that we're going to need for Maclaurin's. We're going to do this example here. We've been given and we are being asked to find count dy by dx. Well, first, a log, so we know that that goes to 1 over 1 minus the chain rule. So we will be differentiating what's on the bottom of this fraction and getting a mark. I now need to differentiate that again, so I'm going to put it into a form where I'm going to find it easier to differentiate. So we will go with minus 1 minus x to the minus 1. I can now differentiate that by considering the chain rule again. So let's do d2y by dx squared. Bring my power down to the front and reduce my power by 1. So I get 1 minus x to the minus 2. Remembering that I'm using the chain rule, so the function that's sitting inside the bracket will differentiate to give me a minus 1, so it's minus 1 minus x to the minus 2. Or minus 1 over 1 minus x squared. Now I'm going to differentiate again, so I want the third derivative this time. Again, I can use the chain rule, and I can use the first arrangement of the function. So multiply by my power, reduce my power by 1, multiply by the differential of the bracket. So I have my third derivative. I now need to answer the question by considering its value when x equals a half. d 3y by dx cubed, when x is that value, will be minus 2. 1 minus half is half cubed, which simplifies 2. Minus 2 divided by 1 over 8, which is minus 16. Now, I've done this using my log rule for differentiation followed by 2 chain rules. I could equally have applied the quotient rule at this stage or here, and I would have got perfectly valid answers that way. So that's question 1, introducing the idea of multiple differentiation, often involving different differentiation techniques. Right, we're now going to have a look at example 2 on page 14. So in this case, we've been given a function and we're being asked to come up with a third derivative again. But this time they're asking us to use function notation because this can often shorten the working quite considerably, and you will see that it's later linked to differential equations. So we've got f of x. Again, we have a chain rule differentiation. Our first derivative, using function notation this time, e to the x differentiates, sorry, e to the x cubed differentiates to e to the x cubed, but I need to multiply by the differential of the function sitting inside the exponential. So, because I'm applying the chain rule, I need to multiply by 3x squared. That means that my result is 3x squared e to the x cubed. Now we know that e to the x cubed is f of x, so we can write this as 3x squared f of x. Now, the reason for doing that is because I can then use this form of the first derivative to help me to come up with the second and third derivatives. So let's have a look at part B. That's our part A there. So our second derivative. We are now differentiating this function, and I have 3x squared times a function of x. So I have a product. That means I need to apply the product rule. So the first function is 3x squared. That stays as it is. We then differentiate the second function. If I differentiate the second function, I get f dashed of x. I then differentiate 3x squared and get 6x. I leave f of x as it is. And so I have the result for the second derivative, which, as you can see, matches the second derivative that they asked for, obviously written in a different order, so let's rearrange the order. F of x plus 3x squared dashed of x. Okay, so that's part 1 done. Part 2, I'm being asked for the third derivative. So I use the function notation in the same way. This time I've got 2 product rules. Okay. So working with the first one, leave the 6x as it is, differentiate f of x, and we get this. We get f of x. Differentiate 6x, get 6, leave f of x alone. Working with the second term, 3x squared left alone, f dashed of x, the first derivative, is differentiated to give me the second derivative. Differentiate 3x squared, we get 6x, and the first derivative remains unchanged. So I now have 4 terms. I can now collate those that are of the same format, so the 6f times the first derivative. So this becomes 3x squared second derivative plus 12x times the first derivative plus 6 times f of x, which is what we have been asked to find. So that's multiple differentiation, and it's working with function notation, which I'm sure you can appreciate simplifies the working quite considerably. We're now asked to deduce the values when we sub 0 into each of these. So let's do that. Part C. So we are being asked for f first derivative with 0 subbed in. So that will be 3 0 squared times by f of 0. F of 0, subbing it into the original function, it's going to be e to the 0, which is 1. So this becomes 3 times 0 times 1, which is in fact 0. Second derivative. Six times x times by f of 0, which is 1, plus 3 times 0 squared times the first derivative, which is 0. So again, we have a result of 0. You will find that you get a lot of zeros when you are working with functions of this type, but they are not all. So the third derivative, when we sub the 0 in, is going to give us 3 times 0 squared times by 0 plus 12 times 0 times by 0 plus 6 times 1. So we have a value of 6. And that is demonstrating how we can work with multiple differentiation to obtain higher derivatives, and also the fact that we sub 0, which we will need when we come to do Maclaren's. Just one point on notation. You may see f with either Roman numerals or the actual number there. So f of 3 with 0 would be an equivalent way of writing the third derivative of with 0 substituted in.